Flight 4 is the last of our flight test programs. This shot of the underside of the vehicle stacked on the pad. One of the most significant things at this point is that we turn this vehicle around from one flight to the next in something on the order of 3 months. That kind of a turnaround rate was done in spite of the fact that we had all of the scrutiny and all of the thoroughness of a flight test program, and yet that same rate will carry us through the ops era for the next couple of years. You see a couple of cats in a pressure suit. This is also the last time that you'll see anybody wearing a pressure suit or using ejection seats. From now on, we're going to be going in shirt sleeve environments. Come out to the launch pad. One of the things we did here was to, as Hank mentions, we get ignition on time, much less than a second off the planned trajectory. Here you see the engines coming up to speed. The engines are controlled in the final count by the onboard computers. We verify that we have good main engines prior to ignition of the solids, which commit you to flight. Just prior to this, we had loaded the payload on the pad, which is another first for this part of our mission, and that's going to be one of the ways we streamline the turnaround time for future operations. What you're watching now are pictures that show the umbilicals coming away from the tanks. These are the ones that are used to keep the tanks topped off, keep them full, and as a way of controlling the venting. Here the spacecraft is lifting off, going past the tower. Throughout this part of the ride, from this point on, you're looking out Hank's window as we do our roll down range. This is the vehicle turning. It launches with its tail to the south, and then we roll to pick up whatever launch azimuth we need, in our case a 28.5-degree inclination orbit. Throughout this part of the mission, I was very impressed that the ride on the shuttle is much like it was in the Saturn. One of the major advantages or differences, I would say, is that you have more acceleration getting away from the pad, and the vibration levels are reduced.
We see the vehicle here going through approximately Mach 1. You'll notice that the shock waves start to build up around the nose of the vehicle and the tanks. You can see that quite vividly. We're somewhere over 20,000 feet now, and speeds building very rapidly. This is the region of maximum dynamic pressure. Here's a view taken from the pilot's window as we pop through the atmosphere. It's very dramatic as you get out of the atmosphere, and the sky begins to turn dark very rapidly. 8.5 minutes from liftoff, we're some 58 nautical miles high and traveling at just under 26,000 feet per second. Here's a view taken in orbit as we do one of the OMS burns that I described to you earlier. We did 2 of these burns to get into the 130-mile orbit, 2 more to jack the altitude up to 160, then a 5th one to adjust the entry roll phasing. Here's a just brief look at the operation of the continuous flow electrophoresis system. This is a prime example of an experiment or an operation that can only be performed in 0G efficiently. It must have the space environment. The principle of operation is that biological materials assume their own inherent charge in the presence of an electric field, and that serves as a basis for separating these materials. This can only be done now in the laboratory, and only very small quantities of biological materials that can be used in the treatment of disease can be separated in this fashion. It could be done with a static device, but to increase the yields, you need continuous flow. The principle being to put the biological materials in solution, pass them between the electrodes of an electric field. The molecules with a larger charge would then have the largest lateral displacement in the field as the flow proceeded. Now, the big enemy of doing this on Earth is gravity. Gravity limits how much or how concentrated the solution is with the materials you're trying to separate, because the solution must keep it in, must hold it up, and in gravity, if you get the concentration too high, it won't hold it. Gravity also plays a part in convection. As the fluid is heated by the electric field, convection currents set up, which destroy the purity of the sample being gathered, and also affects the quantity that you can separate. In the space environment, you can increase the yield several hundred times over what you can do on Earth. And this is extremely important because then this allows us to generate clinical quantities rather than just experimental quantities. The big factor here is the cost. To produce the same amount of material on Earth as we can produce in orbit under a comparable period of time would cost a fortune. So space use of this type of device is going to reduce the cost and make the materials available. This is the first of 6 flights flying this device under a joint agreement between NASA and the contractor. Our first results show that this device worked very well, and the results are very promising. In the future, we may very well have factories producing biological materials using this same technique. And again, I say the importance is that it can only be done in a space environment where there's no gravity or very little gravity. The device is run, a little microcomputer. Here we see the pilot making an input into that computer. Here's a shot of an upfire in jet and side firing jets. This is the kind of firings we took the data on, as I told you, with the plume survey. There's one of the small vernier jets firing. We took that picture from the elbow camera on the RMS. The RMS was utilized in 2 days of our flight. The RMS is a sophisticated device. It works very much like your own arm, in which the brain computes the drive rates for the different joints to make the arm do what you want it to do. In the same fashion, the computer computes the rates with which to drive the arm. Here we see an example of how you can roll a payload about its own longitudinal axis, yet not make it translate. You can do the same thing in similar fashion by causing the payload to go up and down with respect to the orbiter, or we can make the payload go back and forth parallel to its own axes, as you see here, without rotating the payload. So it's a very versatile and useful tool.
This is an example of donning the lower torso of a spacesuit. I'm wearing a liquid-cooled garment that provides cooling when you're outside. The pictures are taken inside an airlock that's in the back of the spacecraft cabin on the middeck. The airlock is something we've never had before. It allows you to go inside, and the hatch you're looking at is an exit into the payload bay where you have the vacuum of space. Inside, you can go in a shirt sleeve environment, don the suit, check it out, and then translate outside without having to depress the major part of the cabin. The purpose for this exercise in STS-4 was to prove that we had good mobility inside the airlock. And you've just seen me put my feet in a set of stirrups that are going to anchor my feet so that I can simulate opening the hatch into the payload bay. This was in preparation for STS-5, where 2 crew members will come inside, close off from the cabin, depress the airlock, and go outside to perform an EVA.
Here's one of the prime reasons we go into space. Not to have fun, but the presence of zero gravity. Imagine the applications of this. We've already talked about one, the CEPAS, in which we use the lack of gravity to do something very useful in technology and production. But you could also use this to, say, process materials in which it's important that the materials not touch a container with which that it's in. The lack of gravity also has some disadvantages in that you must somehow anchor yourself if you want to work in space. Here, the crewman puts his toes under the edges of the locker, and notice he has quite a bit of freedom then to move about without coming loose and floating around as you saw earlier. Another device we evaluated was this little foot loops that he's put his foot in. Just a little loop, hooks his foot under it, and then he's able to make some movements. A third device we looked at are these little sandals with suction cups on the bottom. We evaluated this for several days during the flight and found them to be very useful. We probably still need to do a little more development on them, but the concept is sound. One of the devices we liked the most on flight for improving morale was a treadmill. It works exercise works in space just like it does on Earth. It clears your thoughts and makes you ready to charge again. We had a harness that's attached to the lower torso, and those bungee cords there applied a force equal to the body weight. So your legs were seeing the same forces they would see in 1G on the surface of the Earth. We also had an electronic device that run off a battery you could attach to your earlobe. Was also attached to the treadmill. You could tell what your heart rate was, how far you'd gone, how long you'd been running. This was a real morale builder for our flight, to be able to use this.
One of the things we took a look at in our operational evaluation was some revised packaging of the food system. In order to save weight and space on the spacecraft, we have gone to dehydrating the food, putting it in some plastic containers. Now, Hank is on the left side of the picture putting water in to hydrate it. You mix it up. Since most food tastes better if it's warm or if it's cold rather than ambient, we have this aluminum thing that looks like a suitcase. It's actually a little portable heater. Put the food that has to be warmed in there, and then we'll put it off to the side for 15 or 20 minutes and let it warm up. At the same time, we had a little refrigerator, which we carried for the first time on this flight. Then we could put beverages and things in there that would be cooled. And you put it all together so that you have a hot meal with cool beverages, and it goes a long ways towards making the food a lot more flavorful. And just as it does on Earth, having a good meal does a lot to bring up morale. And when you're working 15 and 16-hour days, that's important.